So today's talk is a foretaste of the new book. The title of the talk is What is Special About Autocatalysis?
Thank you very much, Stefan, for the kind words of introduction, and also thanks to the organizers for inviting me. Also, I'm not really a member of the community of chemical networks. I prefer to work on rather simple systems, in particular those where you can also make use of analytical expressions. The title, here we are. The title, what is special about autocatalysis? I want to convince you that autocatalysis is not a simple process, not a simple thing, and I hope you will, at the end, believe there is quite a number of things special about that. I put my talks on the webpage, so if you are interested in the overheads or the transparencies, they are on the webpage already. Also the link I was unable to do this morning, I will do next morning. There you can see all the details. Now, I have several topics. The first one is autocatalysis in chemistry is kind of an introduction, and it should make you convinced that chemists don't like autocatalysis for several reasons. The next thing is the batch reactor, then comes the flow reactor, and we shall see a number of special fluctuations which are typical for autocatalytic processes, which you commonly don't find with other processes. And then, guiding over to biology, there is the logistic equation. And this logistic equation, also, it's a very simple thing, and it's very old. It's older than Darwin's work. Is in a way combining features from both here. And then at the end I will say a few words on natural selection and how autocatalysis is involved in natural selection. Now let's begin with autocatalysis in chemistry. I mentioned already briefly that chemists don't like autocatalysis. In particular, autocatalysis which gives rise to nonlinear phenomena like oscillations, pattern formations, and so on. It's easy to understand why they don't like it, because chemistry until the middle of last century has been very much technology-oriented. And when you produce a compound, you don't like to have it in the reactor and half an hour, when there are oscillations, there is another compound in the reactor. So this is counterproductive for doing chemical work in chemical engineering. The other thing is that these reactions are quite complicated, as you will see, and so there is no real easy access to kind of analytical work on realistic higher order reactions. Of course, what you can do is you can make models, and autocatalysis is very favorable for doing models with interesting properties. Nevertheless, the observation of oscillations and the notion of autocatalysis is quite old. It was Wilhelm Ostwald, who was also a Nobel Prize winner and who was, many people say, the father of catalysis, so he was devoting most of his work to catalysis. He wrote about autocatalytic reactions the following definitions. Reactions that show an acceleration of the rate as a function of time. And this he did 10 years before the turn of the century. Now, what he wants to say is, I will explain here in equations. This is one of the simplest autocatalytic reactions that you can conceive of. I have a resource A, then a molecule X, and by a process it happens that this molecule is copied and reproduced, so I get 2X. Now if you write down dx over dt, it couldn't be simpler than that. It's K times A times X by mass action, and here we have an A, and if we have a closed system, then the number of molecules is constant. So it is, as a matter of fact, because we have this kind of conservation relation, it is an equation in a single variable, and X, as a result of this process, can only increase, and when X increases, the rate increases, and this is what Ostwald wants to say. Now, in this case, of course, you can calculate, you can integrate, and you get the function which gives you the time course of X. Everything is very, very simple, and here you have a plot. So this is X increasing until everything has been converted into X, and A is going down until A is 0. This reaction shows one important thing, which we make use later on. X equals 0 for this reaction is an absorbing barrier, in the sense that whenever X becomes 0 for some reason, then nothing will happen in the future, because dx over dt is 0, and so x of t equals 0. And this is something that we shall see then later on in stochastic models to be one of the important problems. Now, autocatalysis, you can be more general and just be quite innocent and write an n here, then you get n plus 1 here in the autocatalysis. This gives you a number of problems. I will illustrate only one here. First order, this was the reaction that we have seen already, and I will show you by the end of the talk that there are a number of quite complicated reactions which overall behave like a first order autocatalysis. And what are the special properties that we get here? Well, it's self-enhancement, as said before already, gives rise to exponential growth. Exponential growth is associated with Darwinian selection of the fittest, and in reality, we have, for instance, PCR amplification that every biochemistry student makes in his lab, which follows this kind of rate law. And in nature, we have the asexual reproduction of viroids, viruses, and bacteria, which fulfill the first order. Now, of course, physicists were not very much interested, and so second order became very popular in the second half of last century for several reasons. It is, if you have two or more, if you have here more than two in the end, the properties are a little bit more strange than for n equals 2. However, in essence, they are the same. So the really big difference is whether you have n equals 1 or n equals 2 or larger. Now, you have a strong self-enhancement, and this gives rise to hyperexponential growth. And some people in this area have called it nonlinear dynamics. What is this nonlinear dynamics? Well, first of all, you can have oscillations of concentrations. You can have chaos, you can have spatial patterns, and for the fluctuating reactions, when you have small, bistability turns out to be very important. Now, there are plenty of experimental works on oscillatory chemical reaction, Turing patterns, etc. And then in biology there are symbioses which fulfill these properties of higher order autocatalysis. There are two exceptions, and one can easily see why and remember it. In plus-minus replication, you have two autocatalysis. There is an X and a Y, but the behavior is the same as first-order autocatalysis because they are strongly coupled. In case of sexual reproduction, it's interesting because the reason is a different one. In sexual reproduction, as we all know, we need males and females, so at least two. So this would also fall in this category where n equals 2. However, sexual reproduction, I won't talk about that, but that's quite interesting, is nonlinear, but has a kind of nonlinearity which is funny because it has all the properties of a linear system and not that of a nonlinear system. Well, if you want to have a one-sentence illustration why this is so, it's very simple. There is the matrix of the second-order coefficients, and in case of sexual reproduction, this matrix is symmetric, and as you know, symmetric matrices give you a number of nice properties which take you back to the realm of first-order autocatalysis. Now let's consider for a second. Yeah, these are two people who wrote a really excellent article, Nonlinear Chemical Dynamics. It is a kind of review on all the kind of reactions and patterns that you can find. And so now I want to show you some examples. Example number 1, the Brusselator model was one of the oldest models developed by the Brussels group, and it's very simple. There is no reaction in nature that comes close to this model. However, it's such a nice case where you can find all these properties of nonlinear systems in one fairly simple reaction model. It suffers from one problem, and this is an essentially molecular step, 3 molecules involved, and physicochemists hate their molecular steps for a simple reason, because the probability of 3 molecules to meet in a certain instant is pretty small. So the Brusselator is popular, but everybody was aware that it's unrealistic. People around Dick Noyes Field and Koresh in Oregon, they made another model which shows all these nice properties. They have a non-stoichiometric factor here for fitting data. But if you put f equals 1, you get all the phenomena that you are interested in, oscillations, chaos, and so on. Now, this model is not so innocent as you might look at, because there is also a thermolecular step if you go in this direction. But it doesn't make any difference whether you make this reaction irreversible or not. So here you are circumventing this thermolecular step. Now, with this model, you can reproduce experimental data on one reaction which became popular, the Belousov-Zhabotinsky reaction. Meanwhile, there are 20 or 30 different types of reactions which give rise to these phenomena of higher order autocatalysis. And I want to show you, if you do the kinetics of this reaction, you needn't read that. The impression that you should get, in reality, we get an enormous number of individual reactions showing this nonlinearity, and you can you can try to work out a model with all these reactions. Of course, you can simulate it on the computer, but analysis is practically impossible, except numerical analysis. So you play with your constant and you see how the model behaves. This was also Dick Noyes who worked out the Belousov-Zhabotinsky reaction. And just to remind you what are these nonlinear phenomena, there are these kind of waves, all kinds of waves, combining oscillations and three-dimensional motion. And it was a great achievement of de Kepler and his colleagues when he could show that you can get Turing patterns of different types. Just to mention Turing, you will know, wrote a paper very early showing a chemical reaction mechanism that gives rise to spatial patterns. And these are stable spatial patterns. So these are moving and these are stationary. With this, I rather would like the introduction and become simple for the rest of my talk. And simple means I will restrict to first order autocatalysis because there we can analyze much better. And I will mainly restrict to single-step or two-step reactions to make a kind of mathematical analysis possible. Now let's start with the batch reactor. What is a batch reactor? A batch reactor for a theorist in chemical kinetics is just what he does all the time when he assumes we have a homogeneous solution and when we assume the temperature is controlled. Now, experimentally, this is not so simple, so I copied here a kind of a batch reactor drawing. What you see is here the kind of stirrer to mix the reaction to get a homogeneous medium. This is not trivial because here at the edges and of a batch reactor to get real homogeneity is very difficult. But as a theorist, you needn't care, you just assume that it is achieved. And you have temperature control. This is easier, but also not completely easy. And the people who work on devices for doing chemical kinetics, they have quite a hard time to get this as proper as possible. So let's go back to the reaction that we have seen already with Wilhelm Ostwald on the first picture. We can consider it reversible, and you will see in a second why this is interesting. It's again a reaction in a single variable, so everything is trivial. Here you have the solution, and here you have a general property. If you have A equals constant resources, the reactions are of the type, and all the reactions that we shall see coming from very different chemical models, they have the structure. We have a constant times x and a second constant minus x squared, and this gives us the possibility to have two states, and this will be important. The state of extinction, x equals 0, the stationary state, and this is the state I have said, which is important because when you have reached it, it's an absorbing barrier, the system stays always there. And the second state is, I call it the state of reproduction S1, where x has a defined quantity, here gamma 1 over gamma 2. So this is the only commercial I have in my talk. I want to advertise my book. When we go to stochastic treatment, it looks very innocent in this but it has 700 pages. And I learned one thing when I read Phil Anderson's paper, More is Different. I learned it here with this book. I have written books with 200 pages, 300 pages. 700 pages is different. Only making the index and so things with the help of LaTeX, which is a wonderful, really a wonderful editor. But so this is and I have to say I have put perhaps too much into it, but it's really a lot of different reactions in here. Now we come to the stochastic treatment, and it's straightforward to consider in stochastic way. So I rely on master equations as a people to different approaches. So we have our probability that our resource A of t has some integer value, and we have a conservation law, which also holds for the stochastic process. And then we have our A of t, m, which is a kind of integer variable. And, as we shall see, this m, for some reason, can vary. No, we would say, well, why doesn't it vary between 0 and c? No, it varies between 0 and c minus 1, and we will see in a second why. And then x of t is just the variable which goes from 1 to c, also integers going up. And you see the 0 is missing here. Oh, you'll see this in a second. You can write down a master equation. It's always a straightforward example to write down the master equation here for the reversible reaction. Of course, if you let the reaction go only in one direction, then it's simpler. The number of terms is 1/2 from the previous one. So also you are familiar with master equations. It's not difficult to write down the master equation here. In most cases, I have to admit, writing down the master equation is a nice exercise, but it doesn't help you to understand the kinetics of the system, because you can solve only exceptional cases. Now here, with autocatalytic reactions, the only example where there exists an analytical analysis of a master equation is the work by Aslan and Lorenzi in 2008. And you get analytical solutions. But these analytical solutions consist of series expansions, which suffer from the fact that they have the higher terms have very large numerators and very large denominators, and if somebody was doing such sums, he knows what I say. It's nice, you have an exact solution, but for the practical purposes, it's also not very useful. For practical purposes, what turns out to be quite nice is simulation. In particular, since the computers have now huge memories and they are very fast, you can do a lot with these simulations. So our simple reaction, here it's written down, the reversible case and the irreversible case looks like that. And now, let me first look at what's happening now with small particle numbers in case of these reactions. A plus x yields 2x, and the reverse reaction 2x yields a plus x. Now let's assume we have one particle of x. Then we have to undergo this reaction. We get two particles of x. And these two particles of x, of course, can react here or here. If they react here, they give you 3, and so on. If they react here, in this direction, they give you 1. So, and you are back back to the origin, because you have again one particle. You can make two. Out of the two, you can make one, and so on. Now, this is what people in stochastic theory call a reflecting barrier. You cannot go through. You cannot go to the state x equals 0. So this reaction can't die out. Here it's shown. You have here m equals 0. That means all A is converted into x. This is a state. It is possible. You go up to here, but you cannot come to the highest state because your mechanism with single atoms or single molecules doesn't allow you to. So there's something we could keep in mind. The reversible autocatalytic reaction, A plus X gives you 2X, can't become extinct unless there is some additional reaction and so on. But I'm only talking about this equation here. So we have a reflecting barrier. And we remember one thing. We also have an absorbing barrier at x equals 0. However, we cannot come to this absorbing barrier because there is another one before, one molecule higher, that doesn't let you go through. So now if we do the irreversible reaction, we have such a single trajectory that goes from some kind small numbers of x molecules with, in the stochastic process, it goes up stepwise, and you come until you come to the state everything has been converted into x, and A, the resource, is 0. Now, this reaction can't go to x equals 0 for trivial reasons, because the only step which is allowed is to go from A and x to A minus 1 and x plus 1, so x can only increase, as you would also guess from this equation here. But with stochasticity, it looks different because you see the individual points. Now, this is the deterministic solution, the curves that we have seen already, and you see some deviations without cheating. I got this trajectory as the first with a random number generator where I had given them defined seeds. And you will see this is quite untypical, because if we have many of these trajectories, you see there may be a long delay at the beginning before the reaction takes off. How can we understand this? Now, we can understand this quite easily because the time to the first reaction it follows a Poissonian distribution. And the Poissonian distribution has a steep increase at the beginning, then a maximum, and a long tail that goes out very far. And so you see this long tail already here. What does this mean for our process? Here you see, this is again the deterministic solution. We have trajectories which go faster, but the majority of the trajectories, and in particular the time, what you have here, that can be very long, and you are in the flat tail of the Poisson distribution. Now, this is when you calculate, and this is the standard way to analyze stochastic processes. You calculate the expectation value, and you embed it in a band plus minus one standard deviation. Okay, that's what you get. This is 10,000 trajectories, so you see everything is quite smooth and nice. But then, when you look on the deterministic solution, you see the result of the Poissonian distribution. You have trajectories that go out to longer times very fast. Now I have looked in the literature where people have reported this, and I didn't find anything, so I thought I give this kind of phenomenon a term, and I called it stochastic delay. So this is the deterministic solution, which is faster, and here you have the stochastic delay. That means that the majority of your trajectories, you have seen there are few ones which are faster, but the majority of the trajectories is slower. So how can we analyze this stochastic delay? Well, you would say, go to some place here and look at the delta t. And it turns out to be more difficult, but there is an easier way to have a measure of how much the two trajectories deviate. This is the delta x. This is the deterministic, which is larger, and the stochastic, average expectation value, which is smaller. And now this starts here from a small value, and here is a small value, and you just look at the maximum. And so I thought this might be a nice description of this stochastic delay. Now, if you start out the way, then you want to see how it depends, the stochastic delay, on different properties. And the most important properties is the number of initial particles. So you have one initial particle, 2, 3, 5, 7, 10. They were the values I was choosing here. And this delta max, the stochastic delay, this measure of the stochastic delay goes down as we increase the number of initial particles, as we would expect. You see from 13 down to 1.3 here. And the time, if you have more particles, it's earlier. Everything takes place earlier and faster, so this time goes down. And then I played around and said, I want to have a measure for this stochastic delay that is independent of the time and independent also of the number of initial particles. And what I did was quite natural. Excuse me. No, wrong direction. So I said I take this delta x max and divide it by the population size. So this was here, 100 particles was here the population size. And as you know, there's a conservation relation, so this is a constant for a process. And then I saw a certain regularity here, and it turned out when I multiply by the number of initial molecules, I get a quantity which varies very little. So this is kind of trying to find a conserved quantity by experimental technique. You can easily explain that it has to be expected, these dependencies. And the nice thing was then I changed the population size, and that quantity again was the same, even when the delta x value changed by 1 order of magnitude. So I thought it's worth to give it a name, and so I called it stochastic delay. Now, the constant k that you have here, this is, as a matter of fact, absorbed in the time axis. So I can work with the same k, and then I have here different times. But that's all. The time doesn't enter here, so it does not interfere with the stochastic delay. So this was what we can get from the batch reactor. There is one feature: stochastic processes are more slowly than the corresponding deterministic solutions. The expectation value is more slowly. We can find some trajectories which are faster, but they are very few, and the majority. Now let's go to the flow reactor, where we have different situations. So this is a nice drawing. What you do is you make it. It's almost like the batch reactor with one exception. You let your A flow into the reactor and then again compensate the volume gain by solution which flows out of the reactor. So this is our flow reactor, and then you see what was a single reaction before are now 4 reactions, or 2 reactions and 5 reactions, because you get pseudo-reactions. Molecules flowing into the reactor can be written down as a reaction where out of the sky molecules A created. And of course, A and X flows out of the reactor. So you can write down the equations. Now you have really 2 variables, and equations are more complicated. But again, you get 2 stationary states, a state S0, which is the state of extinction. Remember, the state of extinction we could not reach in the batch reactor. And then another state where we have all A and X in certain variables. So now it turns out that one initial condition is very suitable for analysis. And this is the condition I call empty reactor. So I start with no resource. And I have to have X, because X equals 0 means nothing is going to happen. So I have a seeding quantity of X, 1, 2, 3, 4 molecules, and so on. So, and the result that I get is, at the beginning, A flows into the reaction, the concentration of A increases until there is enough A that the conversion reaction starts, and then we go to some kind of stationary state. This is the solution of the differential equation. And sometimes you go to state S0, sometimes you go to state S1. And as it has to be, by the uniqueness theorem of differential equations, if I have here 2 basins of the 2 attractors, the 2 states, I call them here S1 and S2, then there is a separatrix. If I a little bit on this side of the separatrix, I go here. If I a little bit above the separatrix, I go here. So this is a typical example of a deterministic bifurcation. And if you look on the diagram we had before, we can see phases in this empty reactor condition. Phase 1 is A is pouring into the reactor until it reaches a certain value that the reaction can actually start. Then I have a phase, I call it here phase 3, you will immediately see why. In this phase 3, the system converges to the stationary state. And then phase 4, the system is at the stationary state. You have, of course, a deterministic equation goes very slowly, converges very slowly at the end, but for practical purposes, this is already at the stationary state. So remember the 3 phases. Increase of A here, then decision to go to the state. There is no decision because deterministic system is deterministic. So convergence from A and very little X to the values at the stationary state. Now, how is the situation in case of stochastic systems, stochastic trajectories? So what I have drawn here is a bundle of trajectories. There is, of course, no separatrix anymore because fluctuations let the trajectories go from above to below in the previous thing. And this is what I tried to indicate here. What's essential is we have a distribution of trajectories, and this distribution before the bifurcation point is a monomodal distribution for T. This is the critical T where we have our bifurcation. And then after the critical point, we have a bimodal distribution. This curve is the distribution of the molecules, reacting molecules, reacted molecules, and so on, going to state S1. And this is the same for S2. And we get such a bimodal distribution. And this gives rise to what people have called, I give you a reference on the next transparency, anomalous fluctuations. They have nothing to do with thermal fluctuations. They are fluctuations which are induced by the bifurcation, because a monomodal distribution becomes bimodal. And if I don't play tricks, then the expectation value is somewhere here of this bimodal distribution. As a matter of fact, the expectation value tells me nothing, because it's neither the maximum of the distribution going in one direction. No, please. Now this trajectories, they are all random variables. Yes.
T sub C are also random or determined?
Excuse me.
T sub
T no. It is a stochastic process where we have a random variable, and these, of course, jumps at random T values. However, the progress in T is continuous, and it's not random. So it's what actually, it's like in the master equation, where T is a continuous variable, and you have your distribution in your X or A or B or in the numbers of molecules. So T here you have the situation before and afterwards, and time progresses this direction. Now let's look at an example. This is a simulated random trajectory with certain initial conditions. And here I have introduced one more phase. This is phase 2. And in phase 2, and you will see what this means in a second, the system decides by a random process to which final state it's going, to S1 or S2. Can go to both. And in this phase, you find this kind here. It actually happens where the molecule goes. So let me repeat the 4 phases of the stochastic autocatalytic process. Phase 1, the empty reactor is filled with the resource. Phase 2, random events select the state towards which the trajectory converges. Phase 3 is trajectory approaches the long time state. Phase 4 is the trajectory fluctuates around the long time state. Now, this is one example of such a trajectory. And here we converge to a state which is not the extinction state, it's the state of reproduction, as I called it, S1. And here this is the other trajectory. Here the system converges to the state of extinction. So, and this is now many trajectories superimposed, and you can read this easier when I put into it the deterministic solution. These 2 bundles here, red and black, they are the trajectories going to S1. and they fluctuate pretty beautiful around the deterministic solution. And here, up here, I have other trajectories. This is they go to extinction. There is no red molecule there. So I have this superposition, which I was indicating, more elaborate as the bimodal distribution. So now you can do some kind of counting. Trajectories going to S0 and S1. If I have a single molecule at the beginning, a single X at the beginning, X0 equals 1, I get most of them becoming extinct, which is pretty clear. If I have one, I need only one act to go from 1 to 0. Or if I have already gone to 2, I need 2 elementary steps to go from 2 to 0. So if you increase to 2 molecules, 3, 4, 5, you see that goes down pretty much, and for 5 you have only 4 to 996 is the ratio of going extinct or becoming going into the reproductive state. One thing is also interesting. If we have now, under a certain constant condition, different K values, so the reaction can be more slowly and the reaction can be faster. So a slow reaction, this is K equals 0.01, stays very long here and then goes up. A faster reaction, this period is smaller, and here the period is very small. Now, what would you expect when the trajectory sits very long in this small? Then I would expect more go extinct, and this is precisely what happens. What you see is for 0.01 for the case, very small case, stays long near 0, none for small population size, no trajectories goes into all go extinct. And if I increase population size as it has to be, then we come closer to the deterministic solution, and the deterministic solution would be 1,000 here and 0 here on this side. And if you increase the reaction parameter, this becomes more production state and less extinction. So let me summarize the fluctuations of autocatalytic processes. Number one is thermal fluctuations. They go with the well-known square root n law, and they are in all chemical reactions, also in the autocatalytic processes. The second case that I wanted to, let's stay here. The second case is stochastic delay. This is something I haven't found in the literature, but I thought it worth to look at it more different. And then anomalous fluctuation in case of bistability. And they were popular in physics and in chemistry in around the 1980s. But De Pasquale, Tartaglia, and Paolo Tombesi wrote a number of papers on that. So these are the 3 types of fluctuations that we have seen here. Now I have to, how much time? 10 minutes? 20 minutes. Yeah, 10 minutes. I want to have questions. So, logistic equation. Logistic equation has a long story, and I found it's very nice and very useful, and I take a result right out here. They show, as you have seen in the flow reactor, we had only anomalous fluctuations with the 2 steady states. In the batch reactor, we had only stochastic delay because of this reflecting barrier. We couldn't go into extinction. And the logistic equation will give us both. But let's do a little bit history. Actually, it was Robert Malthus who was predicting that the geometric progression of people will cause starvation, because a geometric progression increases faster than you can prepare food. Then Euler just transferred this geometric progression into an exponential function, and people are commonly thinking this is a very big advantage. I don't believe that, because if you look, for instance, from small numbers going on from small, the geometric progression and the exponential function with the same rate of increase, they are very, very close. The geometric progression just takes the discrete values, and in between there is very little difference. So whether you say geometric progression of or exponential function, it is the same. Now, Pierre-François Verhulst read Malthus' book, and he said there must be a mathematics that I can apply so that I take care of the fact that I don't have infinite resources, infinite nutrition. And actually what he did as a consequence of the finite resources, what he said is, and that's we had already, here I have the term giving rise to exponential growth, and I introduce a negative term which is quadratic, therefore I stabilize my system. And this is easy to integrate. And what you get is this here. This is exponential growth, and this is the logistic growth. You can play with the logistic equation, and please consider here that this was 1838, 20 years before Darwin published the Origin of Species. And just taking the Verhulst equation and thinking about the real population gives you natural selection. I want to show you that. And I never understood why mathematicians did not do it in last century. Here I have my logistic equation. This is the equation, this is the solution curve after integration. And the basic structure here of the equation, as I said already, is x gamma 1x minus gamma 2x squared. And all equations we have looked at so far are of the same type. And now let's make chemical models for this. Now, one chemical model would be the reversible autocatalytic reaction. And with playing a little bit around with an annihilation reaction, I get here 2x becoming extinct. The dx over dt is practically the same. This factor 1/2 comes from the stoichiometry here, but you can make r twice as big, h twice as big, and then it's the same. However, the interpretation is quite different, because in this case you get the reversible autocatalytic reaction with the reflecting barrier. The absorbing barrier we have, but they can't be reached here. And with the annihilation reaction, you can immediately show you can go to the zero. So, the same differential equation, but in the interpretation of single elementary steps gives you very different results, because here you can go to zero, and here you have the absorbing barrier, which you can reach here, and here you have the reflecting barrier, which gives you a completely different behavior, because here you can't have extinction. Now, I can make my story short. When you now look at the logistic growth, compare the expectation value, which is the black curve here, with the red curve, which is the deterministic solution. What you see again is stochastic delay. And then there comes a mystery that I don't understand, because these are two entirely different systems. They're a little bit related, but what you get here is again this constancy, not as beautiful as in the case of the autocatalytic reaction, but this is amazing. The constant value is again almost the same. It was 0.13 something. So I leave this standing here in the room. I cannot explain it, but you get this delta to be a fairly constant quantity, independent of the initial particle numbers and independent of the population size. The same as it was with the autocatalytic reaction. Now, I said I have also a state of reproduction and a state of extinction when I use this annihilation problem. And indeed, you have to count very carefully, because what you see here, I did 100,000 counts in this case. It was 10 times 10,000. And you get extinction 560, 520, when the number of initial molecules increases 12, 16, 1. Did you see something strange for ordinary behavior? Easy to explain. I will do it. Now, we always had, when we increase 1, 2, 3, we had the number of extinct states going down. But here it stays for 2 almost constant. And then going to 3 and 4, it drops. Going to 5, it drops again. Can you guess why? In the annihilation reaction, 2 molecules were combined. So there is no difference whether you look at one or both, and this gives you this kind of behavior. So now we come to my last part, which is natural selection, and I start again from the logistic equation, but now I had, and this is where Halst was thinking, of a homogeneous population, a population of only one variant, and that fulfilled the logistic equation. And what you have to do is nothing but say, I don't have a homogeneous population. I have a population which is distributed over different variants, and these different variants, they differ in the fitness values. So you get this equation, you can solve this equation, and in this equation, you have Darwin's natural selection and the optimization of a quantity, which is the mean value of the fitness. So the mean fitness is optimized in this case. Yeah, this is just the calculations again. And here you see different initial conditions. So the slowest growing molecule has largest initial conditions to make this thing more interesting. For a short period of time you get this. Oh, what did I do? No. So here. And this is for a long time, and you get selection of the fittest. Well, for me it's a mystery, because mathematicians were there, biologists were there. Why didn't they find this prior or at the time of Darwin's Origin of Species? There is no reason not to. And here you can work out the theorem which provides you with this survival of the fittest. You can do the selection in the flow reactor. So what you get here then is you can look at different population sizes. You start from no fitness difference. You get Moto Kimura's result. So this is all stochastic simulations here. three different variants. The red one is the fittest, the green one is the less fit. And if you go to large difference here in the fitness values, you come close to selection of the fittest. But one point, and this is not really appreciated by many biologists who always talk, yeah, but it's not selection of the fittest. There's another variant has been selected. Whenever you have small particle numbers, you have a probability of selection, of probability of being selected. And the variant with the highest fitness value has the highest probability. That's it. And you can have situations where the probabilities are widespread, so less fit variants are here quite frequent. And you can have situations where the fittest is here in very high amounts. I see. Yeah, no, I'm already late. I can leave this. This is on plus-minus replication, and you get results here. And then at the end, as I promised, I want to show you that also simple autocatalysis, X goes into 2X, is not a simple reaction. This is the simplest case that we know. It's known as PCR replication. You have a molecule of digits, and you can make the complementary strand. However, there you have to play a trick, because if the strand and the complementary strand are attached together, they won't melt. In case of, they won't give you individual molecules, they stick together too strongly. In case of PCR, you raise temperature, and other molecules, other systems like viral systems, they play the trick that they use the double helix for finding the minor strand only a small piece, and then they separate. Charles Weissman in his famous article, Making of a Phage, described that. And then you have actually, as a matter of fact, very complicated many-step reactions in plus-minus replication. So these are several thousand steps if a molecule, if a RNA is 1,000 bases long. And Christoph Biebricher, who unfortunately died very young, found something very important. Whenever you have the right conditions, these complex reaction networks behave like a single autocatalytic reaction. And that's the reason why you can apply results from these small one-step elementary processes. So I have briefly some concluding remarks. Autocatalysis is commonly not represented by single elementary steps, but appears as the result of complex many-steps reaction networks. Complex autocatalytic processes in reaction networks often give rise to simple overall kinetics under suitable conditions. And that's the reason why it's meaningful to work with these simple reactions, because you can apply it experimentally if the conditions are fulfilled. And my last part was the major part, as a matter of fact. Fluctuations in autocatalytic processes consist of stochastic delay. This, I have said, is a result of the Poisson distribution of the elementary acts which have these long tails. And second, anomalous fluctuations which come from different steady states besides the common thermal fluctuations. And with that, thank you very much.
Yes, we have time for a few questions.
So, yes, thank you for the nice talk. You said at the very beginning that chemist people don't like autocatalysis because of the rise of complicated dynamics. But other way around, so if we are interested as maybe mathematician in this kind of dynamics, as for example oscillations, we should consider then catalysis, autocatalysis as crucial, friend, very good, or
you have to ask Christoph Lamm, because he has complicated many-step reaction mechanisms, and he is looking for autocatalysis, usually hidden in certain cycles, and is looking on these autocatalytic cycles. There is no way to prove that whenever you have oscillations, at least I don't know that anybody was able to show that. When you have oscillations, then you have to have autocatalysis. I guess it's very difficult to prove, but maybe somebody comes. The other way around is also not true, because as I told you, sexual reproduction is a perfect model for higher order autocatalysis. However, no oscillations, because the matrix of the coupling coefficient is symmetric and has some simple properties. So it's difficult. One can say if you have a autocatalytic cycle, many step, and it refers to higher order, then the generic situation will be that you get oscillations. But you cannot go to the court if you have such a system and it doesn't oscillate.
Questions about the stochastic delay.
Yeah.
So I understood that you collect simulation curves and then you do statistics of the curves per time point. So in the vertical axis, you take the average, and then the line that you get is different from the deterministic line.
Yeah, yeah.
So my first question is, if you took the average for one value on the y-axis, then you would probably get exactly the...
I have done. It's much more difficult to calculate, but this is a technical reason. There's nothing in principle. I have done it, and I got the same result. So if I again calculate, now you have to modify the quantity because you have a delta t and not a delta x, but you get also a constant. Yeah. Oh yeah, the delay is the same. In one case, you look at on the horizontal, and the other way you look at it on the.
And my second question is, do you know what properties of general properties of the stochastic process will lead to such delays?
Yeah.
Irrespective of chemical.
Yeah. So my guess is that this stochastic delay is a result of two things. When you go from the deterministic to the stochastic solution, first of all, you have this distribution, the Poisson distribution, which says that you have this long tail, and when you average times or something like that, it's not the same thing than when you calculate the integral and you get a bias there. This you can easily show. But I think there is another feature behind, which is equally important or even more important. When you have a deterministic solution, every smallest increase, 1/100th of a particle, 1,000th of a particle, give rise to autocatalytic enhancement. That's not true for the stochastic reaction, because it stays at 0 until it makes a jump by 1. So this would be a result of discretization. So the discretization is not symmetric with respect to this expectation value. But I found it as a fact. I just found it in the curves. So the interpretation is is subtle.
One more question? So, just a comment. I don't know if you ever thought about, kind of a more general version of catalysis, but I don't know. You talked a lot about the, one molecule of X somehow makes two molecules of X, right? But you could have one molecule of X make some molecule Y, and then Y makes two molecules of X. Or a more general version of that. X makes something, which makes something else, makes something else.
Yeah, okay.
Overall,
okay. This is what you can get in networks. You have many, many steps, and then if you look at the system as a whole, you can and there are, perhaps very well how to do that, looking at the stationary state, eliminating variables, and so on. And when you are lucky, you are ending up with one of the simple overall equations. They give you the behavior of the network under certain conditions. And the conditions are when your assumptions are valid. For instance, the assumption of the rate determining steps. So there's one step is rate determining, and all the others just modify the outcome. So in this case, there are conditions. So if I have different values of the rate constant, it doesn't work. Doesn't apply. And so you can have under certain conditions how your rate constants are and so on. That it simplifies to such an the kineticists say overall kinetics, because you have eliminated certain intermediates and so on by making assumptions that they are in vanishing concentrations only present and so on.